Welcome to another tutorial on basic organic chemistry. Today we will discuss three examples of nucleophilic substitution with an extraordinarily high stereoselectivity. First example, the starting material has two tosyl groups as leaving groups. Sodium hydrosulfide is the nucleophile and it is added as one equivalent, only one equivalent. We are starting with a meso compound. This is also meso because in both molecules we have a mirror plane. So the thiolate will make first substitution either here or there. As this should be an SN2 process, this takes place with inversion at the stereogenic center. So this could be the one intermediary product. Well, actually, this will be a racemate, of course. And in the second step, the thiol is deprotonated and a second nucleophilic substitution will take place intramolecularly, again with inversion, and therefore with a extraordinarily high selectivity we will obtain the meso product. Second example. Here we start from a mixture of stereoisomers. The bromine might be located either in axial or in equatorial position. We have a mixture of diastereoisomers. As the product, we will receive the substitution product substituted by methanol, by methanolate, and catalyzed by a Lewis acid. And the methoxy group will be exclusively in an equatorial position. There might be a couple of reasons for that the equatorial position is preferred in this case. However, there is a special reason, a neighboring group participation, which is responsible for the very, very high selectivity of this reaction. So, how can we explain that? The Lewis acid activates the bromine as the leaving group. A stabilized carbocation will be formed. A carbocation at this position is stabilized by a mesomeric interaction with the ether electron pairs. But we have an ester in close proximity, and here an interaction can take place. I try to make a drawing of that. So Here we have this ether, this ester oxygen. Here the interaction with the carbonyl, and then we will obtain that stabilized carbocation. And this is still a good leaving group here, of course, but in the meantime it is blockading an approach of the methanol from this side, and only from that side the methanol can approach this molecule, this reactive intermediate, and it will lead highly selective to this stereoisomer. We started from two stereoisomers, and we end up with one stereoisomer of the product, and therefore this reaction is called stereoconvergent. On the other hand, here we started from a single stereoisomer and obtained only one stereoisomer of a product. In this case, we call a reaction stereospecific. Let's talk about the third example. This is also rather interesting. We start with one enantiomer of this iodide, and although on the first glimpse we would think SN2 process with cyanide as the nucleophile should give an inversion of stereochemistry at the reactive center. Nevertheless, we obtain a product with obviously retention of a stereochemical information. How is this possible? Again, a neighboring group effect is responsible for it. We have a base, and the base will deprotonate this acid, this carboxylic acid. Then, intramolecularly, a substitution can take place. The iodide is substituted as SN2 process, inversion. A three-membered ring is formed as reactive intermediate, and then the cyanide attacks and makes a second nukleophilic substitution. Twice a double inversion leads to an overall retention, and this is what we observe in this case. Thanks for listening.